got this, Adrian.
Thanks.
Okay, let me share the Zoom. Okay, we are live.
Alrighty, so welcome everybody to the Time Scavengers and IODP Expedition 402 live to do this. So with me today are Jen Bauer. She's my Time Scavengers co-president and co-creator. I'm Adrian Lamb, also co-creator, co-president of Time Scavengers, and we have Tessa and Larkin with us here today, the outreach officers on Expedition 402. So they're in the middle of the Mediterranean Sea right now off the western coast of Italy, drilling into rocks and sediments, and they'll give us a ship tour today. So I'm going to turn it over to you two to start the ship tour and tell us what you're doing out at sea.
All right, thank you, Adrian.
Thank you.
My name is Tessa Peixoto.
And my name is Larkin, and we are the outreach officers for the JOIDES Expedition 402.
And we're really excited because we're going to show you the ship, the outside of the ship, and also the inside and all the cool laboratories and scientists we have doing really cool work out here. But just to start off with, a really great view. And what I love about this view is it really looks like we're in the middle of nowhere, but we are actually 5 hours away from Italy through transit. So it's really, we could touch it if we wanted to, but this is the view that we want. And then let me just share my screen just to show you on a map where exactly we are in the Tyrrhenian Sea. And so, as you can see, we're kind of like Adrian said, we're off the west coast of Italy. We left Naples on February 14th, and now we're in the middle of the Tyrrhenian Sea, specifically in an area called the Vavilov Basin. It's the deepest part of the Tyrrhenian because it has some really cool mantle rocks that a lot of our scientists are interested in. But let me give you some background about the ship, just so that we all are on the same page. So I'm going to share a picture of the JOIDES Resolution, which is a 45-year-old ship and has been doing scientific ocean drilling for a while now. So this is the ship in front of Table Mountain in Cape Town. The ship is about 145 meters long, or about 460 feet. If easier, you can think of it as being 11 yellow school buses long. And then you can see the most unique feature we have on the ship, which is our drilling tower, or the deck. And it is what makes us a specifically mission-specific scientific ocean drilling ship. There's this beautiful tower right in the middle. And we're going to see that today. I'm going to show you it up close and personal. And then this ship is part of a bigger program called International Ocean Discovery Program, which has been running for a long time. And this is our map that shows you all the locations where we have been drilling. But this program has been evolving. International Ocean Discovery Program is our newest version of the program, but it's gone all the way from, it started with Deep Sea Drilling Project with a ship called the Glomar Challenger. And then we had to move on to another ship, which is the JOIDES Resolution, which came in with the Ocean Drilling Program. And through time, it's been evolving into becoming a more internationally based program where communities around the world can participate on expeditions where you see the little dots here on the oceans. So we've been in the Pacific, we've been near the Antarctic, we've been near the Arctic, we've been in the Atlantic, and we've been even in the Indian Ocean. And like we are now, we're in the Tyrrhenian Sea. I'm going to pass it over to Larkin to tell you about why we're out here specifically in the Tyrrhenian Sea.
Yes, why in the Tyrrhenian Sea? First, we need to understand a little bit about the mantle. So I'm going to give you a metaphor. In science, we like to use food to explain things a lot of times. So today we're going to use pound cake. We're going to think of the mantle as a chocolate chip pound cake with little nuts and fruit bits and all sorts of things in there. And then because the reason that it's like the mantle is because it has a lot of minerals in it. The mantle has a lot of minerals that melt at different temperatures, just like this pound cake. So imagine if you put the pound cake into a microwave. When you took it out, the chocolate chips would be melted. That's much like how it is when the crust opens up and then the mantle comes through, and then it cools down like the sauce, and that would be like the chocolate chip salt, right? Sauce. Right, that's step one. Another reason that we do the Tyrrhenian is because we have seismic evidence showing that we have mantle intact. What we really want is to think about the pound cake again, that metaphor, with the chocolate chips still intact, which is really unusual to find. How did that happen? When we think about if that mantle, that intact mantle is my fingernail, right? As the crust is pulling pulling, it gets exposed. That's what we want. And that happened millions of years ago here in the Tyrrhenian Sea. Italy, the boot, used to be closer to Sardinia millions of years ago, and they pulled apart. Then that pulling, it tore, and that's where we get the impact from. And then the other reason that we chose this area is because it is so young. Unlike the Pacific Ocean, that's 150 million years old, the Tyrrhenian is like 10 to 15 million years old. So way less sediment deposits. That's the point, is that there's less sediment deposits. That's really important when you're drilling. If you're drilling through thick layers from 150 million years, that's going to take a lot of time. Our equipment just isn't there yet. But with the Tyrrhenian, those layers are only down to 10 to 15 million years, which makes it a lot easier for us to collect the mantle or seaweed. And that's why we're here.
Thank you, Larky. And so that just gives you a brief overview of why we're out there and why all these scientists have chosen to come out here for 2 months where we don't touch land, we don't see land, we don't dock. So they're really committed to getting these samples and really doing analysis in the moment. And they'll be able to answer bigger questions like, what was the previous climate like 15 million years ago, or 2 million, or 10 million? And other questions like how salty was the sea, how dry was the sea, how much was there fresh water or not? So they get to answer big questions like that once they get those rocks or sediment.
And it can help us answer questions in the future, like what could the climate help us with climate questions of the future and other things like current systems and things like that. So there's a lot of answers out here. That's why we're spending all this time in the middle of nowhere. Nice. Very excited.
So now we're going to take you over to the bridge just to show you we'll make sure the ship is actually safe where we're going. So we're going to walk through the core lab. This is Sean Yu, our paleomagnetist. We'll come back to him later. And so we're going up to the bridge through the core lab. So we're just going to have to go up these stairs. As an outreach officer, we kind of get access to a lot of picnic areas. What, Adrian?
Oh, I was going to say, I'll just take a quick minute to say while y'all are walking, if anybody watching has any questions, please post that in the chat, in the YouTube channel chat. We'll be monitoring those and we'll answer questions towards the end.
Yes, please. All right, so here's our bridge, and I'll let Larkin take over.
So on the bridge, we have the ECHO system, the radar systems, as you can see. Wide spaces, there's always somebody up here to cold watch. We also have something special called dynamic positioning. Now this is key for the operation because we have to hold the ship steady. We have usually around 3,500 meters of drill string dangling from the ship. And so to have that, it's connected to the seafloor. To have that, we have to keep things in a tight position. We have what's like what I said, dynamic positioning, 5 pods on the ship. They're thruster pods, and on each one of those pods, there are 2 thrusters below. So when we get to a location that we know we want to drill at, we lower the pods down, and those pods will start to hold up our position. Not only do we have those 10 propellers on the 5 pods working together, we also have 2 mounted propellers on the back, along with our main propellers. So that's 14 propellers holding us in place at one time. And of course, that takes a lot of skill, particularly our captain and the officers up here at the bridge, our dynamic position officers, and they keep us safe. Now, when we go to inclement weather, sometimes we do have to pull up with the drill string and stay safe for a while, because although we have 14 propellers, if the waves are big, we still have to be safe. So there are times when we have to shut down operations for a little bit. But usually, even in weather, and I've been on a lot of ships, this ship is very, very still. My background is as a sailor, and so I've been on many ships over the years, and this is one of the most still ships. A lot of times, we don't even realize that we're on a ship. One of the things you usually can't do on a ship is run on a treadmill, because if you run on a treadmill on a ship and you're in the waves, it's crazy, like you will fall off. Here, you can run on a treadmill almost any day. Just fine. Just to give you an idea, our limit where we start to kind of question weather is about 4-meter high waves. That's when the captain, the DP team will start to kind of call the drilling operations team and be like, maybe have to change some things. And if it goes like if it looks like it's not gonna clear up sooner, they might just pause rather than completely exit out of the hole.
So it really just depends on how the drilling team and the sailing team work together.
We have a question.
So now we're going to,
oh
yeah, go ahead.
We have a quick question related to the dynamic positioning. How long does the ship have to remain in position while drilling?
It depends on how deep we are, how deep we're going to be drilling. So if we're going 3,000 meters down, we would be in that position. It would take us longer than it would if we were only going down 2,000 meters. So it's situational. I'm not sure if that's the question.
We use dynamic positioning no matter how long we're drilling or not. Like if it's going to be 3 days of drilling, we're going to be dynamic positioning for 3 days. In dynamic positioning, there is like wiggle room, like there's like a circle around the ship in our like graph of safety. And so the first circle kind of says, if the ship moves within this area, we're fine, we don't have to change anything. If the ship leaves that first circle of safety, that's when the drilling team and the sailing team work together to potentially say, we might have to stop operations because we're pushing our limit. So the way we determine that is that diameter of the circle is determined by 5% of the sea depth. So that's where Larkin is saying the depth kind of changes how often how wide our safety net of wiggle room with the current and the wind is for that dynamic positioning system.
Cool, thank you.
Any other questions?
Not yet.
So far, thank you.
Okay, all right. So now we're gonna head over to the rig floor, but on our way, we're gonna stop by the lifeboats. Okay.
This is the doorknob.
Sure. So it's the doorknob. That's our doorknob and our handle. So all the doors on the ship are weather tight. So they essentially seal on the outside of the door to make it make sure that like no rain or wind or any humidity kind of like enters the indoor spaces. They're not watertight. They frequently say it's weather tight. All right. You want to tell about the lifeboats?
These are the lifeboats on board. Once a week we have a muster drill where everybody comes up here, puts on their life vest, and make sure that we have the count. The count is up here. Everybody goes checking off our names. So we all have numbers in our name. If we come up here, we get checked off. Now, if it was a real emergency situation, this is where we go. This beautiful, comfortable lifeboat. If you could, like, you might be able to see it here a little bit. It's a little bit. We're getting a little bit salty out here, so apologies. Our windows are a little bit salty. But yes, each one of these has 70 passengers. Comfortably or not comfortably, 70 passengers. So we have 4 of those, and then we also have life rafts on the ship. We have and each life raft holds 35 to 25 people. With all of our life rafts and all of our lifeboats, we have 410 seats and we have 120 souls on board. So no matter what happens, we're covered. Now the reason that we have so many of these life rafts and these lifeboats is because if the ship, say something happens on one side of the ship, well, all of those lifeboats are gone. We're going to go to the other side. And if they have to the front of the ship, got to go to the back of the ship. So you always want to have a plan A, B, C, and D when you're working on ships. And in addition to all of these, there's also a fast rescue boat on the top deck. Can't see right now, but we use that if there's a man overboard to lower that down with one of our lovely cranes, and then buzz on out there and get our man overboard, bring it back home safe. Exactly. And just fun fact, they are orange because orange is the easiest color to see against a blue background. So once we get out, if, for instance, if we had to use a ship, it'd be easy for the, let's say, rescue team to find us against the blue background. And then again, just this beautiful view. It's a wonderful day. We're actually really excited. It was raining yesterday for you, so luckily you made it just in time for the sunshine. But here's the most exciting part, our derrick. Dun, 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 dun. She makes all this possible. Yep, she does. So let's get a little closer. And then want to start here so we can show the shucks? Yeah. Okay, so right here is what we call the shucks. Now think of the shucks as, well, they all have different drill bits in them. And think of this like this is our big our big drill, a big screwdriver, or a big drill, and then those would be the bits. It's like a bit box, but 100 feet tall. And they can open up and they hold these metal barrels that are specific to how we
core. So instead of having them stored, let's say below deck or in another area that's harder to get, they are right next to the rig floor, which makes it easy for us to pull them out as we need and then put them back in a substance called propylene glycol. It prevents them from rusting or eroding, so we can hold on to them for longer. And next thing I would like to show is that there are two floors to our operations. The rig floor is right there, where you'll see a lot of people dressed in red and a lot of machines colored red. But right below, you might be able to see just sort of this empty space. That is where the moon pool is. And the moon pool is, in fact, a hole in the ship. But it's meant to be there so we don't sink. It is there because it allows the drill pipe, when it's mounted in the derrick, to go through the ship in a direct path to the ocean floor. And so that is what allows us to actually deep sea drill. We don't have to go around the ship, we just go through it. And there are doors that cover the top of the hole or the moon pool, so when we're walking, we don't actually fall in, but there is a ladder just in case. But the doors are always closed around the pipe, so we are okay for walking around that area. But let's get closer to the rig floor, because that's the excitement part.
Safety first always. So we have our hard hats and our glasses. Whenever we go past, I don't know if you can see, but there's a yellow and black line right there. That indicates that we are in a work zone, and we need to have our hard hats and our safety glasses on.
And sometimes it's a fight for the good safety glasses.
All right, so it's gonna be kind of hard to hear, but I'm gonna walk you through what is happening right now. Okay. So behind it, you can see that the pipe rolling out. What's gonna happen is they're gonna bring a pipe up to these blocks, this pipe elevator. We're gonna hook it into the pipe elevator, and then it's gonna raise this all the way up to the top. And each one of these pipes is 98 feet or 28.5 meters. So they raise it all the way to the top, and then they can tighten it up. They bring what's called the iron rough net, right? This red machine. They bring it, they scoot it over, and then they tighten it up. Because it can't just be hand tight. We need it really, really, really secure, right? 3,500 meters of pipe. We need to make sure it's secure. So that comes over, it screws it in, and then this guy brings it down, and then the whole process starts again. And that sound came from the winch that holds the entire weight of the drill string. So this is our very powerful winch right here. You can think of this like string, like straws. We're putting straws together, right? So you got one straw coming in, they screw it on, pull it down, another straw comes up, screw it on, and then it goes down. And that would be the same process if we're exiting a borehole. So right now we finished drilling, so we're putting this stuff away. So they're using the top drive to pick up the pipe and put it into the pipe elevator and then back down onto the pipe rack. So whatever you do to start is the same process we do to finish. So let's go down to the core deck and we can talk about coring. And just so you know, the reason we're able to drill and sail this ship is because of our partner called CM Offshore. They're the ones that give us the crew with the expertise to drill and sail, and mechanic and an electrician and so on. So we really need our partner CM Offshore for this. They're the backbone of this operation. These guys are amazing. They can drill anything. They can drill anything. So what happens when we have a sample, the core is ready to come out of the sample? We have 5 people that are standing here waiting to pick up the core. And each one of these samples becomes their type of experience. These plastic long tubes, each one of those is about 10 meters long. So one person isn't going to carry that to be by. So what they do is they'll be standing here and they start loading up. As they load up, they walk down. They walk down the catwalk and walking. And she's walking backwards right now. It's very impressive to see. All right, so we're walking, and then when they get all the way to the end, what they'll do is they'll put it down on these flats. So we can see right the example. Here, I got a photo as well. So that is our core liner, but here is an image of what a sediment core looks like on these wrecks. So our marine technicians are the ones that carry the core and prep the core for the scientists. So let me go back to Morgan so she can keep showing you. So this is our mini example. What they would do is they would set it down to this. They make sure they measure it out and make sure that they've got their 1.5 meters. And then once they have that, they're going to take this really cool cutter And what's so cool about it is it's got a little blade right there. You can see. Now this didn't exist before the JOIDES resolution. This is something they invented on board. And that's what happens a lot when you're working in an operation like this. You have to get really creative. If you see something that doesn't quite work, but you have an idea of how you can make that better, there's engineers on board. We even got a 3D printer on board. So we can create so much stuff on here with just an idea. It all begins with the idea, right? So what we do is you take this and then we latch it around here. It'll close. You just turn it and boom, that's your sample. Perfect.
And all of that is possible. So here's the thing. So we have a drill pipe that goes through the ship down to the ocean floor. And then again, just to show that image just one more time to make sure we're on the same page. So we have the ship on the surface. We have our drill pipe that goes through the ship to the ocean floor, and then it starts drilling. And it starts drilling using a drill bit, which is a specific cutting apparatus for different seafloor formations. So a sediment drill bit would be different from a hard rock drill bit, which is exactly what we see here. This is our soft sediment drill bit, and as you can see, it's a little bit wider and has a lot more space in between the rotary cones, but our hard rock has less space and the hole in the middle is less wide. And it's just to ensure the recovery for hard rock is increased versus the recovery for sediment is increased based on the drill bit they use. This hole is to help you understand where the core is actually going. These rotary cones and the drill bit cut the borehole, but inside there's something called a cutting shoe that for soft sediment punches through sediment and collects everything through that core liner, which goes in the middle. So the cutting shoe is around this core liner, it punches through, and then when we go to pick it up, we send a hook through the drill pipe to pick up the core, and we bring it back up to the core deck, which is where we are right now. But the drill pipe stays down the whole time. So things are moving inside the drill pipe up and down while the drill pipe stays where it is. So we have the core barrels that are in the shucks that Marcus showed us earlier. And then we have the drill bits at the end of the drill pipe to help us have things go through and come out when we're cutting. Any questions, Adrian or Jen, in the chat before we move on to the labs?
We do. We have one question. When is the core cut in half? One for curation and one for archive inside the wet lab. So when is it cut in half?
So it is inside the core lab, which is through this door that Robbie's holding for us. Thank you, Robbie. So the core is a whole round out on the core deck, and it comes out looking like this. This is some cores that we have collected. And you are seeing sediment, probably for this sediment for the first time in a few million years, which is pretty cool. So this is called a whole round. So it has not been cut yet when it gets to this area of the lab, which is the physical properties lab. But it does get cut after it goes through all of these different machines here, like the natural gamma radiation, thermal conductivity, the Wormsel, which is a multiple sensor logger, so it has like magnetic susceptibility, P-wave, which basically just shoots sound through it, and X-rays. So it does physical properties with whole rounds, and it will go into the slicing room after it goes through all of those machines. So it has not been cut once it enters this room just yet. It gets cut when it goes onto that side.
Perfect, thank you.
So let me just show you the slicing room just to kind of finish the question. So they are slicing something right now. Our marine technicians are the ones that handle the core up until this point. So they are using a wire cutter to cut the sediment, because if they use a saw, it would really turn up the sediment too much. But if it's a hard rock, they'll use the saws. So you can see an example right back there. Those saws allow us to cut the hard rock samples into those two halves. But I do have Brandon, who helps in the physical properties labs. Can you tell us about the X-ray machine?
Yeah, absolutely. Yes, my name's Brandon. I'm on the physical properties doubtful measurements team. So basically trying to understand the link between the physical properties of the rock and then all the other aspects of the rock properties that we can observe, like its composition, its structure, and all those things tell us about how it formed and the evolution of the basin where we are. So yeah, I can show you some of the tools that we use. Cool. So yeah, after after the cores are split, one thing that we like to do is take X-ray scans of them. So this is very similar to where you go to your doctor's office. You have something wrong with your bones inside, and the doctor needs to be able to see inside to understand what happened to you. So very similar with the cores. If you just look at the surface of them, all you do is get a very nice picture here, but we want to be able to actually image inside and see if there's some particular structures that are interesting. So maybe you can see this is a sedimentary core. Some of these clasts here, maybe they're aligned in a particular way that says something about how the sediments were deposited. Or for hard rocks, we've actually been imaging the fractures that tell us about the stress state and how those rocks were broken in the past and then filled in with various different minerals. So how this works is we have our machine here, and we can load our cores in. Scan them.
And this X-ray machine is actually quite new. Our older one is on the opposite side where I showed you over there. Our older one is over there that does a 2D image. This one helps us get a more 3D internal image of the structures.
The hole to put it inside. And then we can come over to our machine here. So we're just doing a section now and go ahead and scan it. And so what this machine is doing is it's basically, there's a mission side where it's shooting X-rays. The core is laid out across here in this tube, and then it's going to run along. And so it's emitting X-rays, and then there's a detector on the other side. And right now it's just warming up, just taking a second to use it in a bit. And basically, the detector on the other side will see how much X-rays pass through the material, and that tells us about the density. So the more dense the material is, the more of those X-rays it's going to attenuate. And then at the end, we're going to get a nice picture, and we can see that the denser areas are darker, meaning more attenuation, whereas the lighter areas are much less dense, meaning a lot of the X-rays pass through and they made it to the detector. So here our scan is going along. We get a raw image, and then we can do some formatting as well to try and tune the settings as best image the different structures that we're interested in. This was a sedimentary core, so maybe we're interested in the features of the sediments, showing how it was deposited, for instance. And another big thing that we observe on these images is drilling damage. So let's see, let me try and lighten this up. So these lines here are actually a part of the drilling process, and they create these biscuits and gravy pattern. I'm not sure if you've talked about that yet, but this interesting pattern that you see in the rocks. And it's also helpful to know which features are just related to the drilling and which features are actually related to the initial deposition of the rock, so we don't potentially misinterpret some feature as having geological significance when it doesn't. It's just an artifact of how we were able to recover them. So you can see that we have lots of this artificial stuff from the drilling, but we also get these really nice dense areas, which are those larger clasts that I showed you before, and fractures that show up as these less dense areas, and then a big transition that we have here into the more clay-rich sediments at the base of this core. So we have a really interesting transition between this finer grained material here and this denser material, which has larger clasts that are likely more volcanic material, so it's absorbing a lot more of the X-ray material. So that's an example of how we use this machine to look at soft rocks, but we'd also do it for hard rocks. I actually have an example here. I have to exit out of this image. But here's an example of some of the imaging that we were doing for hard rocks before. Here on the right, you can see these are some of the mantle rocks that we were finding, and all of these dense areas are fractures that have filled in with calcite veins. So the fluids were going through the rock and then deposited other material in those veins, and all these different orientations of fractures tells us about the past twisting and crunching and all the things that have helped break the rocks and deformed them essentially in the past.
And why is this wonder?
Yeah, so this one's darker because this was the settings that we had for imaging sediments. And sediments are much less dense than harder rocks. And so when we had those previous settings, and we were also doing it on the whole round, so before the core was split, so the x-rays have twice the amount of material to pass through on the whole rounds. And because this machine is more optimized for imaging sediments, basically all the x-rays were getting attenuated by our hard rocks. So we had to, one, increase the power, so try and get more power of x-rays to make it through. And then two, we were doing it on the split cores on the hard rocks, so that we reduced the amount of material for it to go through. And we were getting much better images. You can see absolutely nothing before, and then after we were getting some really good scans.
Awesome. Thank you, Brandon.
Yeah, we have
Any
questions.
questions?
Yeah, we have a few. Okay, so is it a 2D or a 3D scanner?
That's a great question. So this is not, unfortunately, like a really amazing three-dimensional CT scanner where you can actually get volume information. But what's cool is we can use it at different angles. So even though it just gives us a 2D pixel image at the end, we can rotate it and do it at different angles and get a series of different 2D images to essentially kind of look at the 3D structure and orientation of those. So we don't have a way of getting like a very nice detailed three-dimensional image because it's not the highest resolution machine, but we can take the 2D in multiple different orientations, which gives us a pseudo 3D structural, tells us about it in kind of 3 dimensions.
Oh, that's neat. Okay, so our other question is, what are the file outputs like from the scanner? Do you get multiple images from one core, or is more like a flatbed scanner versus a CT scan of your head? So basically,
the outputs from each scan.
Yeah.
Yeah, so the output from each scan is essentially a grayscale image here. So it's just a scan of the whole core liner and has associated pixel value. So that's basically just the intensity. And so you get this grayscale image, and then there's a lot of processing that you can do to best highlight the density range of your material. So oftentimes it picks up on the core liner, which is not dense at all, and it kind of disturbs the rest of the image that you can see. So we have to manually drop out the core liner and do other sorts of processing to the images to try and make them look as best as we can.
Awesome. And the XCT scan, is that done later?
XCT scan. So this has an option to do a semi-CT scan, as I was mentioning before. It can rotate and you can do it at many different angles if you wanted to do that, but it's not the highest resolution, so it's not going to give you a 3D, like a box, what you would call a voxel, so actually like a 3D pixel. So yeah, it's more just we're using this to get 2D images to look a little bit about the structure and then compare it to the core images that we're also scanning.
Perfect. Thank you, Brandon.
Thank you, Brandon. So now we're going to go over here. So a bunch of physical properties on that side of the lab, but we have this area, which is the core description area, where we have the working half that comes over here, where everyone can put their tags in the sediment cores. And this is our favorite one. Ash wanted to really make sure one of our scientists put a face on his sticker so that he could indicate which samples are his for fun. And so they basically come here and say oh, I want this area. Oh, yep. I want this area of the sediment, or I want that area or that area, so that they can do their destructive analysis of these samples. So things that would make the sample no longer as original as it was or completely used. So that's the working out. But I come over here to my sedimentologist, Lorna, who also works with the archive tabs. So tell us about what you do with the archive tabs.
Hi, I'm Lorna. I'm photography Austin. So as I said, I'm the onboard sedimentologist. So one of the first things we do when we get the tools onto the archive table is we need to image the rivers here called the shills. So this takes high resolution photographs along with the whole of the core. The reason we do that is because one of the most important things to measure as sedimentologists is the color of the core. And much like an apple, when you split an apple in half, it starts to change color on the surface because of the reaction to oxygen. The same exact thing happens with the core. again bring it onto this table or this table again. And then we start to look for things such as grain size changes, like I said, color changes, because that can really indicate what's going on in the environment and how sedimentation is changing through the length of the fall. So as you can see here, we have this kind of black, very coarse grain material, which we think is volcanic rich. And then we transition into this much more paler material where we can't see the grain size of it, and this is typically monofossil ooze, so background pelagic sedimentation. So that's what we do macroscopically, and then after we describe the core, we come over to this machine, which is called the schnizzle. So this is another way of measuring colour. It does R, G, and B, so red, green, and blue, and it gives us coordinates upon that scale as to what the actual colour is of the core. And it also gives us magnetic susceptibility. So if there's any magnetic minerals within the core, we'll be able to see spikes on the graphs produced. So this measures at around a 2 centimetre resolution. So this one takes quite a long time to produce. And these are some of the other cores we can get in, which are really cool. Like here, we can see some big class of mud, which may indicate some slump deposition. So the sea floor is not very stable within this area. So everything I described is what we can do macroscopically on the cores, but actually a lot of those colour changes and grain size changes will be due to maybe hygienic components or things within the core that are changing that we just can't see. So we come over here and we make a smear slide. So we take a very fine amount of material, so on the end of a toothpick, and we smear that along the slide, and then we put an adhesive on top. And then we come over to our microscope here, which is when we can see like what is actually within the sediment we're describing. So, for example, we saw some green areas on the core. So, what we can see when we look microscopically is that we can see these green minerals here. This is called glauconite. So, this is when clays change diagenetically, they turn into glauconite, and that is what we're seeing in the green. We can also see here these shards with very sharp edges and sometimes lines within them. And this is actually volcanic glass. So within this area, we have a lot of volcanic material, and we're actually seeing it even in the background sedimentation, which is really interesting. And then in terms of biogenic components, we have a lot of foraminifera in these samples, which is amazing because this is what I study, so it's really nice to actually see them in the material. So these are benthic foraminifera, so the ones that live in the water column, but we're also seeing benthic foraminifera that live in the seafloor as well. Can you say the difference between benthic and benthic, just in case? Yes. So benthic foraminifera typically live in the top 200 meters of the water column, whereas benthic foraminifera live up on the surface or in the surface of the sediment at the bottom of the ocean. Any questions for Laura, Adrian, in the chat?
None for the chat. I have one, Lorna. So are you all doing like point counting methods or anything like that to like quantify the amount of biogenic versus like volcanic stuff in the sediments?
Yeah, so we're looking at each sphere slide individually, and then we're classifying it in terms of percentages of what we're seeing. We haven't actually got time to go into too much detail on kind of what minerals we're seeing, but we are classifying it in terms of biogenic silica, biogenic carbonate, and silicic material.
Awesome, thank you.
Thank you, Lorna. All right, so that was the sedimentology area. So again, let me just show you up close the sediments that they're looking at. So this is what you see after we x-ray and cut it. So it's just really interesting. I always find interesting the different colors that show up in the sediment. Because in my head, I'm like, yeah, sediment, but we got brown, we got green, we got some grays, yeah. I think textures too. And the textures, yeah, it's pretty fun. Luke is our other sedimentologist. But we have Robbie, who's our micropaleontologist, who looks at foraminiferas.
Yes, I do. But do you want to show what Chanyu does first?
We'll go to you first because I'm next, and then I can show Chanyu.
Cool. So, that's why I'm laughing, just showing you how the workflow is like. But for me, it goes a different way because I like it that way. So, so what happens is, as I showed you how we get the core on the catwalk, and core is cut and then it goes around the analysis lab. But for me, what usually happens is there is a core catcher with that comes along, and I go there to take the material that comes from the core catcher. I get it here to my own lab, which is the best of the ship because I have the view. And what I do is the dirty work first. I use this apparatus which has been designed by Fabricio, a technician on board, an awesome guy. And I just put the sediment on the sieve over here. It's a 63 micron sieve. And I just wash the sediment. So all I have to do now is turn this on and it starts rotating and it washes the sediment away. And then after the sediment has been washed, I put this extracted sediment in the oven for drying. I put it for a while. And what I do after the sediment has dried up is go to my microscope. This is my awesome station. I get the sediment here, put it under the microscope and extract the foraminifera. I work with plankton foraminifera, so I extract them. And what my basic job on the ship is to extract plankton foraminifera that have been observed in different depths of the sediments and give an estimate of the age they were deposited in. So what I usually do is there are different species of foraminifera which were deposited at different time periods. I just analyze them and give an estimate of the age. So that's what I do. But to get an exact estimate, I need to take the help of John Q, our paleomagnetist on board. So what he usually does is he does the paleomagnetism magic, and what he looks for are reversals. So I have to tie in my dates that I'm seeing with his reversals that he's finding and try to get an age estimate first. So we'll go to John now.
Yeah, let me just show what a plankton foraminifera looks like under Ravi's microscope. So it first starts to look like this, and this is what Ravi's doing on that tray. He's like looking for these shapes out of grains, and then once he finds these, he'll isolate them and potentially put them into our scanning electron microscope, which basically takes images of really microscopic things, so you can really see the details on the shells of these organisms, like how many dots they have, how many conical shells they have, and so on and so forth. So this is what he's looking at.
Yeah, I'm looking at planktonic foraminifera. No, it's plankton foraminifera. So yeah. Cool. So yeah, that's what I do for a living on the ship. So yeah.
So now let's go over to Sean Yu. So that was the micropaleontology lab. This is the paleomagnetist lab. So he has multiple instruments. He has one that is a section half magnetometer, which you can see a section half coming out of it right now. It has a little track that holds it. But essentially, you can see the track will run through and my image went away. The track will run through the machine. Thank you, Shani. It'll run through the machine, and there's different magnet sensors on each parts of this area, and it'll run the core through it back and forth so it can get a general idea of what magnetic signatures exist, like the reversals that Sean, you were saying. But then I'll let Sean, you introduce himself. What kind of research do you do on the ship?
Well, I'm magnetic minerals and how they can record the change of geomagnetic field. And what we can do is to study the magnetic properties of sediments and rocks. So what we care about on the ship is the sequence of the magnetic records, like whether they are pointing up or pointing down. So this like a compass telling us the direction of the geomagnetic field during the formation of the sediments. Yeah.
And that's when you work with Ravi to determine the
Yes. So like we are a team, and we need to confirm each other with different evidence. Yeah.
We no longer call it reversals. It's either a youngster or a Ravi.
Yeah.
They have fun. Thank you, Shania. Thank you, Ravi. It's someone back there? Okay. So the other part of this micropaleontology side is that there are microscopes for thin sections. So when we get hard rocks, we have our lovely petrologists here that look at the microscopic features of the hard rocks. So they do the same thing that the sedimentologists do. They look at the macroscopic version of the hard rock, and then when they find something really interesting, they want to look at that under a microscope. But do either of you want to tell us why we want to look at it under a microscope?
Okay. A lot of times these rocks have very small minerals, and also they have experienced really high temperatures and fluids that have altered their initial composition. So it's really hard for us to see macroscopically with our eyes. First, what was the initial minerals in the rock because they're so fine grained, and then second, how these initial minerals have been altered and changed to a more stable mineral under the specific temperature and heat conditions that experience. So Toma here already very kindly for us a thin section under the microscope. So this is a very, very thin slice of rock, as thin as one of your hairs, 30 microns thick.
And so let me repeat that. So we have the thin sections on those glass slides. They get sliced to a hair-like strand almost. Extremely thin, goes under that microscope. This microscope is connected to a camera, which connects to this computer, which allows us to take images and save it for later. Sorry.
Yes, no, exactly. And this is the image that we're looking at, and all these are different minerals, and look at the polarizer, and you can see all the beautiful colors. These colorful dots make our EU's petrologists super happy because this is the mineral olivine, and this is what we want to find, because this is one of the initial magmatic mineral grains that have been actually being preserved in the rock, and this is really exciting for understanding the initial primitive composition of the mantle.
As you can see, Topo is the most
These are igneous petrologists, and mantle rock is his focus. So that's the reason why he's on this expedition particularly, because he wants these samples. And like we said earlier, these samples are really hard to come by on land. To give you an idea, the mantle under New York City is about 30 kilometers below continental crest. So that would take forever to try to get to mantle. And then even then, that mantle is altered from weathering and erosion. But this mantle is pretty intact under the Tyrrhenian Sea because it's pretty young, like we said, 50 million years old. Anything else that you would like to say?
No. Thank you. This is the most serious I've seen.
Thank you, petrologist. So, any questions, Adrian, before I move on?
No further questions here. Anyone have any questions in the chat? Any viewers want to ask questions? We'll give them a few minutes, but if y'all continue, and I'll let you know when we get to another breaking, like a little break point.
So this is our core lab where it has different sections to it, like the physical properties, like the core description, like the splicing room, like the micropaleontology. But downstairs is where we have additional labs. But before we go to the additional labs, we have a pet wall. And this is where we put our pictures of our pets to basically say we miss them, but we love them and share a bit of cuteness. And then on the other side of this wall is our expedition logos. And these expedition logos are created by the crew. And by each expedition, like toward the end, they start to have competition and the crew votes on which expedition logos they want to represent at their expedition. So it's really neat to see the history of each of the expeditions, but also sort of the character that comes with each crew, because each crew changes per expedition.
This was in 1985. It's like it was like one back in time.
Yeah. Here's the 1985 one. So down below on the foxhole deck, we were on the main deck. We have three labs. We have the
one more question. Sorry. What are some of the biggest minerals that we found in cores?
Sorry, say that again?
What are some of the weirdest minerals that we found in cores?
Weirdest. So this is a funny story. So zircon's not the weirdest one that we found, but zircon was something that was making our petrologists kind of go like, wait a minute, there's too much zircon in a core, in one of the thin sections or smear slides. They're like, this is too much. So then they did a quick experiment on the drilling mud to see if the drilling mud was potentially incorporating some zircons into the core that they were sampling. And they were able to find out that a certain percentage was being introduced from the drilling mud. So it allowed them to not date the rock by the zircon, but use something else to date the rock. So I wouldn't say that's the weirdest, but it definitely made everyone like raise their eyebrows a little bit.
Yeah, that's funny.
And then, yeah. And then some other minerals we've been seeing, like olivine. They love olivine upstairs. Tomo, I don't know if you saw, had an earring that was green to represent olivine. And then there's like pyroxene. There's another one that starts with a C, clinopyroxene. So they've been seeing a lot of rock that are pretty tied to mantle, so they're feeling really confident that we're drilling in the right places that we want.
Awesome, thank you.
Yeah, thank you. So geochemistry lab, but then we also have two labs here that are run by marine technicians. This is our XRD lab where we want to see the X-ray diffraction of certain minerals or certain samples. This basically is one way to learn about the mineral makeup of a certain sample. Again, just to kind of help us confirm like what's in the rock that we're looking at or in the sediment that we're looking at. This is our thin section lab, which again is run by a marine technician, who's not in here, but he makes those thin sections that Tomo and Edie look at. So just to give you an example, here's some practice rocks that he has, but you start out with a big chunk, this regular chunk, and then they'll cut it into sort of like a thin slice. They'll glue that onto a glass slide. They'll glue the chunk onto a glass slide and then cut it into a thinner slice like this. And you'll probably think, hey, that's pretty thin. It's not thin enough. It actually has to be polished down until it looks like this, so that it can go under a microscope that can increase to like 20 times magnification. So this is his thin section lab. He has different materials and tools to help him polish things down and cut. So again, some scientists, yeah, go ahead.
Oh, sorry. So have you all seen any evidence of major like storms or earthquakes in the core samples or in the thin sections themselves?
Have we seen evidence of storms or earthquakes?
Mm-hmm.
Slumping and faulting is what Ravi is saying. Do you want to explain that more?
From the sediment point of view, we are seeing a lot of nanofossils and microfossils being reworked. So they are either coming down from down below and getting mixed with the younger sediments. And this is what happens when the sediments come down to a slope and like get mixed on, and this process is called slumping. But this is from a sedimentology point of view. But in the hard rocks, as Brandon was showing you earlier, they do analyze the microstructures and the factors, and based on that, they kind of decipher what kind of tectonic activity is going on in the region, whether it's a normal fault, whether it's a reverse fault, things like that.
And like you heard Lorna say, they are finding evidence of volcaniclastic materials, so it does help. And then when they see turbidites in the sediment, so things that eroded the initial sediment layer with new stuff, it kind of gives them an idea that there was a pretty big event happening that came through and introduced a lot of sediment, but they at the moment can't say like where from, what it is, or what it was, but they know it's volcanic material. They just don't know which volcano and when yet. So not necessarily earthquakes, but some other interesting events, big events that are causing some churning of the basin.
Yeah, thank you.
Thanks. No, thanks for the question. So in the geochemistry lab, we have also a microbiology lab. So a geochemistry lab where our geochemists will live, our igneous and inorganic geochemists. This is Chi, one of our geochemists. So he's in charge of a bunch of different processes like ICP, looking at elemental makeup of interstitial water, but this is the first tool he will use. It essentially is a press. So we have these canisters that we take chunks of sediment, put it in there.
Very heavy titanium.
And there'll be a filter in this area. And we'll attach a syringe to this canister, which is right here. We'll attach a syringe to that. And the canister will go right here, apply upwards of 25,000 pounds of pressure to really squeeze out that water, which we can call pore water or interstitial water. And in that water, I like to think is like that water came from a while ago. It's not the current seawater. It's water that has been moving through the sediment for that length of time it's been layered and compacted. So that holds key information of previous climate, previous sea conditions, and other things that he will look at on his multiple equipment, like the ICP-AES, alkalinity, and I forgot what that machine was called, G. Oh, that's ICP? IC. That's just IC. Ion chromatography. And then do you want to talk about your research on the ship?
No, my research is about abiotic organic synthesis and on the seafloor. So once again, where the origin of life on Earth, and scientists have proposed the hypothesis that the life may be here on the seafloor.
Cool.
Are you
And
also
once
looking
again, how about? Go ahead.
Oh, sorry. Are you also looking at like life that may be contained in these mantle rocks as well?
Well, once again, going back to the serpentinization. During serpentinization, hydrogen can be generated. Hydrogen actually is a reducing agent to reduce carbon dioxide and to generate simple organic compounds. That's how the whole origin of life hypothesis starts.
Interesting.
Of course.
So I just want to pause. I do know it is heading to the half-hour mark. Adrian, were there any questions that we should hit before we end the call?
We didn't have any more questions in the chat, but we can give folks a few more minutes to add any. Does anyone else watching have any other questions? Please post them in the chat, and I will ask Tessa and Larkin these questions.
Great. And while we wait for those questions, thank you, G. I just wanted to show you the microbiologist corner. So she has some anaerobic chambers in this cold room to try to mimic the conditions that she pulls samples from in the sediment cores. So she is trying to study the viruses and the bacteria that live in the sediment to see what kind of interaction they're having, but also potentially identify what kind of microbial life lives down there, because it's still unknown. So she has a little anaerobic chamber here, and Milena is over there. Milena, wave. She's our microbiologist. So unfortunately, Milena can't do a lot of analysis on the ship because we don't have enough of a clean room containment for her to actually do her analysis. So she freezes her samples and takes it back home to University of Texas Galveston.
Cool. Okay, we did have one more question.
Go ahead.
How about dissolved gases in pore water like methane and others? They aren't generally lost before arriving to the geochem lab?
Great question.
I have another question. So, in the gases that show up in the water, Adrian, like hydrogen and methane, you said?
Yeah.
Well, the gases we didn't set.
We don't look at that in the interstitial water.
We did, but we didn't find any gases. Yeah.
So they did escape.
Yeah, so maybe low, very low concentration, but they are not, detected.
Okay. What about can you also have another one? How does IODP take care when methane hydrates are recovered?
Do you know what to do?
Of course.
So she performs something called test-based gas analysis, where he basically takes a sample of the sediment, like first thing we get on core on deck. Right. We take a sample, he comes comes down here to our headspace gas analyzer here, and it looks for those hydrocarbons. And essentially, if the range that he finds is out of normal or not what we expect, we literally have to stop. This ship does not have the capacity to handle any hydrocarbon chamber or pressure, because if we were to puncture it, it would kick back and potentially take the derrick off the ship. So we don't want those lifeboats. So essentially, we do seismic data to make sure that where we drill doesn't indicate any hydrocarbon chambers. Then we do headspace gas analysis to also check, and then we also work with the environmental coordination team previous to coming out to determine if the area has any knowledge of potential hydrocarbon chambers. So there's a lot of checking so that we don't go anywhere.
Perfect. We have another question. How many more expeditions will a JR go on before it retires? Before it retires? And how are you all feeling about it?
So we have one. So technically we have two-ish. We have Expedition 403 in June, I think. But we do have a transit in between, which I think will have a School of Rock on board, I believe. So technically 2 trips, 1 expedition. And it is sad, as expected. It's sad. This is an amazing ship. This works with incredible partners like interior staff, who's our hospitality team, and CM staff, who runs the ship. We have incredible partners that have made the ship possible and have just made the crew and previous expeditions and history of science journaling possible. And it is, we're trying to make the best of it, trying to keep doing the amazing science that we're doing, and try to train the scientists on board to just kind of keep passing along these skills once they have to be shorebound.
It's truly a program unlike any that I've seen before or experienced. To have all of these scientists from all over the world coming into one space and making these discoveries in real time is incredible. And they've also created a very inclusive environment, which is another thing that I hate to see go. They're very open and, like I said, inclusive, and they really take care of their people. The CM crew's been on here. Some of them have been on for like 20 years. You know, there's some families that it's father to son. They're both on the ship at the same time. So there's stories here and a lot of history, and it's a shame to see it go. And so yeah, we are. But
there's still hope. Yes, there's still hope. It's not official. There's still hope.
Good. Glad to hear that. One more question. Are there any plans to preserve the Staircase Museum with all of the expedition patches through the years, for the decades?
I don't know. I have to ask the project manager, Emily, to see if she knows. Do you know? I'll find out.
I think they are going to be, all these things are going to be protected in a police station. And they will see, the plan is to, the instrumentation and all will move to Texas A&M. But the museum, maybe there will be a police station.
I'll take care of it in case no one has a plan.
Thank you.
I bet they're doing testing over the stickers. I'll make sure it's preserved.
Awesome. Thank you.
There's actually binders of previous expedition photos, so I'm sure it'll be in the binders.
For sure. Oh, that's great to hear. Those memories will be preserved for everyone. Well, that's excellent. Excellent. No more questions in the chat. We do have an Expedition 02T transit student with us. They're going to participate in not School of Rock, what's the other one? Oh my gosh. Chair Academy.
Yes. Awesome.
And someone said, please say hi to Alberto from Methane Hydrate Nature Geoscience guy, Texas A&M. LOL, he'll know.
I will. He's currently asleep right now, so I won't wake him up for that. But when he wakes up, I'll tell him.
Perfect. And everyone's saying thank you for the great tour. I really appreciate it. And I echo that. This was
thank you for joining, everyone.
Absolutely.
Yeah, it was our pleasure. We had fun showing you all the ship. Like we said, it's amazing. We just want to keep sharing the experience.
Agreed. Yeah. So I'll be on Expedition 403, so maybe we can do this again, and let's just love that.
Yeah.
Awesome. Well, thank you all so much. We appreciate it.
Thank you. Bye, everyone.
Bye, everyone.
Did you want to do a closing?